/Warden/Watson in audit competition platforms. I just started recently doing those part-time, and I am a zero knowledge enthusiast. So I do ZK stuff for now, just for the fun of it.
Amazing.
So yeah, the main problem that or the main situation that we will be starting with is just like a transfer of money. So if I want to transfer money to someone, or if I want to pay for a subscription or a service, etc., I can do it using many ways, using cash, using my bank account, and also using my blockchain wallet. But all of those have some issues with privacy. So for bank accounts, the bank is the centralized part. They can see all my transactions. They can see all the money I transfer, the identity of the receivers too. And when it comes to blockchains, it's decentralized, yes, but it's also transparent, so everyone can see what's happening under the hood. So we have a real issue of privacy here. So basically, everyone can literally track all the funds that we have, and we lose the value of privacy here. So an initial solutions will be to use some sort of a vault. So for example, if I want to send some money to Alice, for example, I don't transfer it peer to peer, but I just input it into or deposit it into a specific vault, and then Alice can withdraw it. So that way we do not have that peer to peer interaction to improve our privacy. But that also can be tracked. So it can be tracked by the man who watches the vault. And if we use a smart contract to do that, it will also be trackable just using the transactions, block explorers, etc. So Tornado Cash have tried to implement the solution. They have implemented many ways or many barriers in order to achieve privacy and to achieve private transfers between two entities. But the main criteria that empowers Tornado Cash is what we call ZK-SNARKs. So ZK-SNARKs is a technique that's implemented, or a technique in the zero knowledge field, which basically allows us to prove to someone else a statement without giving them too much information more than they should know. So the ZK-SNARK is the main criteria that achieves privacy in Tornado Cache, and we will see the technical details about that in the next slides.
Awesome.
So yeah, let's first define some terminology before getting to the Tornado Cache implementation. So for zero knowledge proofs, we basically need a ZKP system that we can give the system many inputs, private inputs, public inputs, and a proven key, and using some mathematical equations we can get two outputs, which are basically the output generated by the inputs that we gave, and also a proof that those outputs are indeed associated to the private and the public inputs. So that's a way that we can use in order to prove statements in a mathematical way. And along the hood, we use arithmetic circuits, which are basically mathematical objects that help us verify the computation that was run in an entrusted system. On the other side, we need a system that will help us to verify those proofs that were generated. So we need a system that we can input public inputs, outputs, and the proof and the validation key. And this system just need to tell us if those inputs are valid or not. And if you notice here, we do not need to give it the private inputs. That's where the zero knowledge aspect is coming from. So we only need the public inputs, the stuff that it's okay for everyone to know about, and the outputs and the proof that was generated, and we can directly deduce if it's valid or not. And in addition to that, a special property about ZK-SNARK specifically is that they are succinct, so we do not have to run the same computation that was run previously by the prover. We only need to do some operations that are basically the logarithm of the operations that were done in the proving process. So next we will move on to Merkle trees, not this Merkle, but this Merkle tree. So basically, Merkle tree is very known cryptographic scheme. So it's basically used to prove that an element is existing in a set of other elements. So here we have an example of four elements: L1, L2, L3, and L4. So if, for example, I know an element L2 that exists in this set, the obvious solution would be to give the whole set to a specific smart contract, for example, and then the smart contract can perform the check on the input that I give, if it's included in the set that was stored before or not. This approach is trivial, but it's suboptimal. So we tend to use Merkle trees to optimize that, both to optimize the storage. So if we use Merkle trees, we improve the storage efficiency. So we do not need to store the whole set. We only need to store the top hash. So how the Merkle tree is constructed, we basically hash all the elements. So we hash L1, L2, L3, L4, and we tend to hash uh, two by two. So we gather two elements, we hash them, we gather the other two elements, we hash them, and we keep doing that process again and again until we reach the top hash, which is called the root in the Merkle tree terminology. So basically, these are the two mechanisms that Tornado Cache relies on in order to achieve its mission, and we will see how exactly it does that in the next slides.
Amazing.
So yeah, here we have a part from the white paper of Tornado Cache. So it's pretty mathematical heavy. So we will be introducing, or we'll be explaining this stuff one by one, so we cannot get overwhelmed by those mathematical annotations. So basically, how it works for Tornado Cache, it is basically the same as the first example that we saw before. So we basically give the money that we want to transfer to a specific smart contract, and then the other party that would like to receive this amount of money, they can basically withdraw it from the smart contract. As we said, there is a problem of traceability, so everyone can see who is the depositor, and then they can link this identity with the identity that have withdrawn the money after. So basically, in the deposit section, so in order for us to deposit a coin, we need to do basically two steps. The first thing is we need to generate two random numbers, which are called here K and R, and we need to compute the hash of those random numbers concatenated. So we concatenate K with R, and we hash those. We compute C, and after that we need to perform a transaction, sending fixed amount of it. So for Tornado Cash, in order to help up with the privacy, we cannot transfer any amount of money. Since, for example, if I transfer 0.001 ETH to the contract, and after that another person withdraws this exact specific amount, that will be a way for someone else to track and to associate those two identities with each other. So we try to eliminate that risk with fixing a specific amount of ETH that can be transferred in a single transaction. So there are multiple contracts in Tornado Cash, and each one of them support a specific amount of transactions. We can if we want to send, for example, 10 ether, we need to go to the exact contract that supports 10 ether. If we want to support 1 ether, we will need to go to the correspondent contract. So yeah, after we generate these randoms, we calculate the hash. We send an Ethereum transaction with the specific supported amount of ETH to the contract C, and we send the C as data. And then this information gets stored in the contract. So yeah, that's basically it for the depositing part. So if I want to transfer 10 ETH, for example, I deposit 10 ETH to the contract, and I also transfer the hash of the two variables k and r, which are called in terminology secret and the nullifier. So in the receiver part, if we have, for example, Alice who want to receive the money I deposited in the contract, the trivial solution would be for her to give us the secret and the nullifier, and then she can withdraw the 10 ETH. However, this is also a trivial option, but it's not optimal for the privacy side. So before I just submitted a transaction deposit with the hash of the secret and the nullifier. So in order for someone to track that, they will just be tracking the withdrawal transactions. So if Alice wants to withdraw, she will be sending a secret and a nullifier. They will hash those two values, and they will try to associate this hash with the correspondent deposit transaction. So this doesn't actually solve the problem, since the nosy person can just analyze the transactions, hash the secrets and the nullifiers, and associate them with the hash that was used in deposit. So that's still not quite the target that we want to go. So the solution to that will be basically to not submit the secret and the nullifier ever in the blockchain. But how can we trust Alice? She needs basically to prove to us that she knows the secret S and the nullifier N without actually giving us the values. And how can that be achieved? We will be back to what we talked about before, which is zero knowledge. So if we manage to if Alice manages to convince the vault that she has a secret S and a nullifier N that corresponds to a specific deposit transaction that was submitted before to the vault, then she will get the 10 ETH I transferred to her. So from a higher level, that's basically how Tornado Cash works. So we use a secret and the nullifier, which are randomly generated by the depositor. Then the withdrawer generates basically a ZK-SNARK proof that basically proves that they know such value N and S that corresponds to a hash that was used in the deposit transactions. Are there any questions before we move on?
Yeah, I do have a question. In the deposit process, do I need to inform the address that will be withdrawing? I don't think so, right? It's just a code. It's just the computed proof that I get to withdraw the money, right?
No, in the deposit you need to specify the address. You don't need to specify actually the address. So anyone that's able to generate a secret and nullifier that corresponds to the hash you submitted before will be able to withdraw.
But during the withdrawal, I'm also able to see another address using a same secret and nullifier, right? So that way I can bound the accounts together. Because to withdraw, you're gonna have to inform those, right?
Can you please repeat? I didn't hear you well.
Sorry. Um, During the withdrawal process, I need to
Yeah.
inform the secret and the nullifier, right?
No, actually, you just need to submit a proof that you know the secret and the nullifier.
So the seed itself.
No, it's not the hash. So basically, the Tornado Cash have implemented the zero knowledge proofing system that you can just give the secret and the nullifier to the system. The system will generate basically what we call a ZK-SNARK proof. This ZK-SNARK proof will then be verified by the smart contract, and this proof basically proves that you know the S and the N value, the secret and the nullifier, without actually making you deposit those values. So
Awesome.
we will be seeing later how it works from the smart contract level.
Amazing, buddy. Keep on. If anyone has questions, just ask, okay?
Okay, I got some questions. Just two. Can you hear me?
Hello?
Yes, he
Yeah,
can hear
hello.
you.
Can you hear me?
Yes, do you have any question?
Yeah, I do. Just want to ask two questions. So
Yeah.
if the user now who deposited the money, I'm thinking Tornado Cash is going to generate a proof.
Mhm.
So that proof you need to notify the person who's going to withdraw it. Like you send the proof to that person. Is that what's going to happen? Then secondly, if I deposit 10 ETH in the vault and supposedly I want to withdraw again, does it have to be 10 ETH also? Can I withdraw maybe a lesser amount or withdraw twice from that same deposit? Does it have to be 10 ETH so I need to withdraw since it was 10 ETH that was initially deposited into the vault?
Yeah, for the withdrawal amount, it is the same as the deposit. So you can only deposit 10 ETH and you can only withdraw 10 ETH. That way, all the transactions will be the same. So no one can have some sort of traceability using the amounts, the transfer amounts. What was your first question again?
Okay, the first question, I didn't really get the proof you were talking about, the ZK proof. So are you saying that if the person who deposits, he puts the two random numbers, he gets a ZK proof. So that ZK proof, are you going to send it to the person who is going to withdraw the money later?
Yeah, for the ZK proof, it can be generated by anyone that has the secret and the nullifier. So, for example, if I want to send you money, I use a specific secret and nullifier. I can give you those values, and then you will be able to generate a proof that you know those values. So, when it comes to the proof generation, you just give it to those inputs to an arithmetic circuit, and this arithmetic circuit will then generate that proof for you. So it is basically just like running a specific script off chain that will take the secret and the nullifier as inputs, and then as an output it will generate the ZK-SNARK proof that you will be depositing into Tornado Cash in order to withdraw.
Okay, so you're actually saying that the withdrawer puts those secrets to the ZK proofs off chain and gets the proof to withdraw the funds, right?
Yeah, exactly. So the proofs are not ever submitted to any third party. So that way you can achieve privacy.
Okay, thank you so much.
Perfect. So feel free, guys, to let me know if you have any other questions. So yeah, but uh, I don't know if you have noticed already. We still haven't solved a problem which is quite common, which is replay attacks. So if Alice can prove that she knows a secret and the nullifier that allows her to withdraw 10 ETH, she can just repeat the same process and get 28 and repeat it again and get 38, etc. So we also have to solve this problem of replay attacks. So if a specific amount is withdrawn, it cannot be re-withdrawn once again. So how can we do that? That's why in the first place we do not have just a random value itself. We have two random values, a secret and a nullifier. So the secret is the secret and nullifier are random numbers. So the why we use two random numbers instead of one, just for this problem of replay attacks. So when depositing, you need actually to transfer not just one hash, you need to transfer two hashes. The first hash will be the commitment hash, which is what we said before, the hash of the secret and the nullifier. And you also need to hash the nullifier itself in order to get a nullifier hash. So we will be basically submitting two hashes. The first one is for the secret and nullifier concatenated, and the second one is for the nullifier hash. So basically, what we are relying on the fact that we just after every withdrawal transaction, we just input we just basically mark a specific nullifier hash as invalid. So if Alice submits a transaction of a proof that she knows the secret S and the nullifier N, we will take that proof, we will verify that proof. If it's correct, then we allow the withdrawal. And after that, we basically take the nullifier hash that was used, and we basically store it in a specific mapping, and we basically expire or make this hash expire. So if Alice tries to do that again, it submits a proof that she knows the secret and the nullifier. We will verify the nullifier hash if it's used before. We basically revert the transactions and prevent replay attacks. So that's the withdrawal the process of the withdrawal that's mentioned in the Tornado Cash white paper. So to withdraw a coin, that's a coin in the Tornado Cash terminology is a specific is basically the n amount of ETH. So if you submit to a contract that has a denomination of 10 ETH, the coin will be equal to 10 ETH. So to withdraw a coin KR with a position L in the tree. So here basically for storage optimization, we are using Merkle trees instead of basic mappings, and also for it's because it's easier to calculate those and to verify the proofs inside the zero knowledge arithmetic circuits. So we basically here rely on Merkle trees for storage. So if you want to prove that you know a specific hash and nullifier, you basically need to prove that the hash of the values you have exist in the Merkle tree that's stored in the Tornado Cash contract. So you basically select a receipt.
One
Any
question,
questions?
Uber, and sorry if this question is a bit off. Would you have an example of the nullifier and the proof? Just because I'm thinking about the possibility of someone brute forcing those, but I don't think that would be quite trivial to do that, right?
Yeah, it's too computationally intensive. It's almost impossible to brute force those. So basically we have numbers that are encoded in at least 200 bits. So you
I
basically
see.
need infinite time to try all the combinations that will allow you to generate the correct proof.
Awesome.
Okay, so the first thing is you select the recipient address, which will receive the coin or the 10 ETH, for example. Then you select because Tornado Cash doesn't have only one Merkle tree, so basically you need to choose the specific Merkle tree that has your hash. So you need to submit its associated root R, and you also need to compute the opening or the branches that are needed in order to prove the existence of your hash in the Merkle tree. Then you need to compute the hash of the nullifier. You need to compute the proof that you know the secret and the nullifier, and then you can perform the withdrawal by two methods. The first one is by executing the Ethereum transaction to a specific contract C, and you give it all the required data. And you can use also a relayer, which will be basically you can give him those values, and he can make the transaction for you, and you can also associate a fee for him. So that's it for the withdrawal mechanism. So basically, this is how it is. So if you have, for example, the Tornado Cash contract of one ETH pool, the user need to initiate the withdrawal, and then the receiving user need to submit a request with the deposited proof. So basically, they need to prove that they know the hash and the nullifier, and also they need to provide a nullifier that was not spent before. So after that, they get their one ETH. So that's how it works, basically from a higher level. But let's now move on to the smart contract size. We will go to the hash
Yeah.
repo of Tornado Cash to see the smart contracts and how they look. So I will basically reshare my screen.
Brother, I don't know if you're on an open mic
Do
or
you have any
something.
question, guys?
Yeah, one question. I don't know if you're on an open mic or something because there's some background noise. But yeah, that's.
Yeah, because there's a problem in my headphones, so I
I
couldn't
don't
use
know, but
them
that's
before.
okay. That's okay. This is still hearable. No problem.
Okay.
One question is, we're gonna talk a little bit about the problem Tornado Cash had recently with the hack. With that create two, right? Wasn't the create two contract that
Yeah,
self.
the hack was basically a problem in the governance contract. So basically, it allowed an upgrade for a proposal to a contract that has self-destruct, which is basically a metamorphic contract. Then it allowed metamorphic contracts are upgradable by nature. So it allows the attacker to change the logic of the contract, then in order to withdraw all the money. So that was the main reason of the hack.
Awesome.
It wasn't related to ZK. It was basically related to metamorphic contracts.
I understand.
Okay, perfect. So do you see, guys, the repo?
Can you make the font a little bit bigger?
Sure.
Thank you so much.
Okay. So here in the sections contract, we have all the contracts that are existing in the system. So we have the first one is ERC Tornado. The second one is ETH Tornado. So basically, Tornado Cash supports ERC20s and also supports sorry supports Ether. And the both contracts inherit from the contract Tornado, which has basically the main logic of the protocol. So basically we have the address of the verifier. The verifier is basically the contract that basically knows how to verify zero knowledge proofs. So in ZK development, we have multiple frameworks that are used in order to develop ZK friendly apps. So we have Socrates, we have Circom. There are a lot of frameworks out there. They provide you with the tooling of basically writing arithmetic circuits, which are mathematical objects, and they provide you with testing mechanisms, etc. So Tornado Cash used Circom, and Circom basically gives you an abstraction of all the logic. So you basically need to just write your circuit, and it will basically give you the proving key, the verifying key, and it will also give you the verifier smart contract that can basically verify the proofs that are generated. So if we here see the verifier.sol, it's basically a contract that's generated by Circom. So it has a lot of mathematical computation. So zero knowledge proofs rely a lot on elliptic curve cryptographic theorems. So those are the things that allow us to have the zero knowledge mechanism and also the succinctness mechanism. So we can verify the proofs faster than we used to the time we used to prove them. So that's we have basically one function that's important in the verifier.sol. We give it the proof and we give it only the public inputs. So we do not need to submit the private inputs. So we just give it the public inputs and it will perform all the calculation and it will return a boolean saying that if the proof is valid or not. So basically, that's a contract that's generated by Circom, and it allows us to verify zero knowledge proofs. So back to the Tornado.sol. We have the denomination. The denomination is basically the amount of ETH that the contract supports. So if the contract uses one ETH, for example, as denomination, here we will have 10 to the power of 18. And we have here a mapping of nullifier hashes. So as I said before, to prevent replay attacks, we basically store the hashes of the nullifiers that were used before. And we have the commitments, which are basically the hashes of the secret and the nullifier that are provided into the deposit process. So in the constructor, we just initialize the denomination, the verifier contract that will be verifying the ZK-SNARKs and the denomination. And in the deposit transactions, we need to do two things. The first thing is to provide the commitment. The second thing is to deposit the money. So the function is payable. You need to give it exactly the denomination, which is what's done in the process deposit function. So here we basically verify that the commitment is unique, so it wasn't submitted before. We basically insert the commitment into the Merkle proof. After that, we store the commitment into the mapping. We call the process deposit, which is defined in the child contract. So if we go to the ETH Tornado, it will be just a safe transfer from. And of course, we have ERC20, so no need to submit any message of value. If we go to the ETH Tornado, the deposit will be just verifying the message dot value to be equal to the denomination. So back to the Tornado. Okay. So yeah, that's it. We emit an event with the commitment and the inserted index of the commitment when we insert it into the Merkle tree. In the withdrawal, we submit the proof, which is the ZK-SNARK or the ZK-SNARK proof that's generated by giving it just the secret and the nullifier. And this is performed obviously off-chain in order to prevent any tracking of those values. We give it the root that contains, or the root of the Merkle tree that contains our commitment hash. We give it the nullifier hash, the recipient who will be receiving the money, and also the relayer if we are using a relayer that will execute the transactions to transfer the money. And here we have the fee of the relayer, and we have refund mechanism.
One question that I have here is,
Sure.
what is the incentive for the relayers? Okay, so to be running, is decentralized? Is this decentralized? I mean, or can anyone run and they will take fees from each one of the withdrawals and everything?
Yeah, it's basically it's similar to that. Yeah. So basically, a relayer is a party that will execute the transaction for you. So it's similar to how permit works in approvals. So in order for you to submit the transactions without a gas, you basically give someone a specific signature, and he will execute the approval for you. So here it is similar with the relayer. The relayer will be the person responsible for submitting the transaction on chain, and he will be getting a fee for it.
Amazing, amazing. And there's also one important factor in Tornado Cash, which is the time, right? That you wait to do the withdrawal, right?
Can you please repeat that?
Sorry. So apparently, the time you wait to make the withdrawal is also very important on Tornado Cash, right?
It really depends. So if there are a lot of transactions happening into Tornado Cash, you can't really deduce that. So, but when it comes to, if for example there are no transactions in Tornado Cash today, and then I transfer or I deposit an amount of money, then exactly after that time you withdraw, then someone can make the conclusion that I deposited the money and you withdraw the money, so they
I
will
see, I
be
see.
establishing the relationship. But if there are a lot of transactions happening into the Tornado Cash contract, the probability of associating two identities becomes a little bit harder.
So I have an interesting question from Infinity here, which is, Can these transactions be front run?
Can these transactions be front run?
Yes.
Uh, I haven't considered that. Let me see. I
I
actually don't know how they are preventing front runs. So
I guess they
it's
prevent front runs because you need the address, right, to do the withdrawal. So the bot will not be able to will not have the same address as you, so won't be able to withdraw the money.
the address isn't really included in the proof. So the receiver address the recipient address you can specify any specific address, but there has to be a way. I haven't thought about it actually. It's quite an interesting question. Mm, yeah, that's interesting. See the refunds. Yeah, I kind of don't see a mechanism that prevents front run here. So the proof can be seen by anyone, the root also, the nullifier hash. So basically, whoever gets it first.
I'm googling it right now, and
Yeah, I would be sincere about that too.
so looks like the generated proof for withdrawing is valid for a single address and relayer.
Okay, but I don't see a verification of the.
Maybe that's done while computing the proof.
I don't know, probably, yeah. Yeah, I'm not sure actually.
Great question and great presentation, bro. Really loved diving into this, you know. And
Yeah, thank you, man.
and the developer he's still in prison, right, in the Netherlands.
Yeah, I hope we don't get in prison too for this talk.
Crazy.
Yeah, it's quite sad to hear that such developers that created some fancy stuff like Tornado Cash are getting in prison for that. Quite unfortunate.
Yeah, especially in the Netherlands, which is a country that's super friendly to crypto, you know, and they also love taxes. I mean, they should see it the other way, but I guess they want to send a message, you know. I have another question is, what if someone submits a very large amount of funds, would he still be able to mask the transaction?
Can you please repeat that?
So what happens if I send a large amount of funds? What is the
Mm-hmm.
best way to avoid people from detecting? Because you know nobody's depositing like 10,000 ether like that. You know.
Yeah, but you have a limited amount to deposit in Tornado Cash. So as we said, you cannot deposit an amount that's different from the denomination. So if you go to the contract and submit your 1,000 ETH into multiple transactions with a specific denomination, no one will be able to detect that's you that submitted those transactions. And you can also use different addresses for those.
Awesome, awesome. More question, guys. Black Hat,
Yeah,
Muhab,
got a question.
Shadi.
Yeah, sure.
Yeah. So was there probably like the KZG for Tornado Camps? Was there any?
Can you repeat the question, please, Shadi?
Yeah, I said, was there a polynomial commitment done for Tornado Cash, and which one?
Yeah, for Tornado Cash, it uses Ground 16. So basically, the ZK-SNARK is a construction is a construction of polynomial commitments and also Oracle interactive Oracle proofs. So when we combine those two mathematical proofs, we get a ZK-SNARK. So under the hood, there are polynomial commitments, but I assume Grok 16 uses KGZ if I am not wrong.
Great question. And
Right,
today,
thanks, man.
I think the current situation is everyone that interacts with Tornado Cash gets blacklisted on Uniswap front end and another major centralized exchanges, right?
Yeah, I guess that's how they are banning people, but it's still, I guess, commonly used, specifically by hackers.
That's crazy. That's crazy.
Yeah.
Does anybody has more questions? Yeah, I think they understood everything. This was an amazing talk. Uber, you wanna say anything else? You have any closing thoughts?
Yeah, I just want to cover a little. I just want to show the circuits that I talked about using Circom.
Awesome. Let's go.
So here's the language that's called Circom, which is basically used to write zero knowledge arithmetic circuits. It's basically the most popular framework, or the DSL language, which is called domain specific language, that's used in zero knowledge for now. So feel free to drop to this section. And to conclude, I would like to emphasize on the fact that ZK is a very promising field, and also a fun aspect to learn. So the applications of ZK into blockchains are getting very high, not just for the privacy side, also for the scalability. So we have ZK rollups such as Polygon ZK EVM. We have ZK Sync era. So we have a lot of protocols that are implementing ZK, and not a lot of people are getting into this field. So this is a promising field, and I advise anyone to get into it. Anyone that's a fan of both cryptography, mathematics, blockchain, this will be the perfect opportunity. So
Mm,
yeah, thank you everyone for
amazing.
assisting, and feel free to reach out to me if you have any more questions.
Bro, I want to thank you so much. This was one of the clearest and best sessions we did so far. And I do agree with you, ZK is going wild, especially ZK audits. They will pay a lot of money. So,
Yeah,
tip for everybody there. And let's do more of those, bro. Whenever you want to come and talk about something, explain something like that, this is really enriching for us, okay?
yeah, perfect. I will be happy to. Thank you.
Okay, thank
Thank
you
you very much.
guys. Bye bye.